Oh. Today we are going to have a history lesson, atomic history. We're going to learn the history of the atom. Yes, Billy.
I hate history. I know it anyways. This is chemistry, not history. If I want a history, I'd sign up for history. There's chemistry. Teach me chemistry. But I know history anyways. In 1492, Columbus sailed the ocean gray.
Well, Billy, no, that's actually ocean blue, so maybe you should brush up on that history. But, Billy, I'm sorry, but we just have to learn a little bit about the atom, the history, atomic theory. Okay, that's historical stuff. We got to learn. We just have to. Well, actually, this is America, Bill. You don't have to learn if you don't want to, but I would recommend it if you want to do well in your assessment. Okay?
Me, I hate this class. Me.
Billy is so angsty. Those angsty teenagers. Okay, atomic history. Let's do it. First person we want to bring up is Democritus. 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 He was one of those philosophizers. You know those philosophizers. You've heard of these people. Aristotle, Socrates, Plato. Okay, all those philosophizers. Smart people. Yeah, smart people. But they didn't do any scientific experimentation. They were just smart people. And everybody went, ooh, you're smart. And you said that, so it must be true. And Democritus, what he did, according to him, he wrote this down. He was walking along the beach, Mediterranean, Greece, Mediterranean Sea, walking along the beach on top of a cliff, looking down at the sand of the beach below. And from his vantage point, his distance, it looked like just a solid tan beach, solid tan. So then he got down to the beach, picked up some of that sand, and he could see clearly, as running through his fingers, grains of sand. So from a distance it looked solid, but up close you could see that there were particles that made up the beach. He had a epiphany. No, not a Tiffany, an epiphany. He had an epiphany. And he said to himself, I wonder if everything is like this, if everything, my coffee mug, my pear, lunch, this meter stick, if it's all the same way for everything, that you can't see, you just see a solid thing, but up close, whoa, look at that, I can see the atoms. There they are. If everything is like that, everything's made up of these tiny particles you just can't see. So he's coined the term, he came up with the term atom. Atom is a Greek word meaning indivisible, with liberty and justice for all. No, not that part, I made that up. But atom is a Greek word meaning indivisible. So an atom to him is some small particle that it can't get any smaller than the atom, but it makes up everything that we can see, but they're just so small we can't see them. That was a great thinky thing that he did. All right, fast forward about 2,000 years. Let's go to early 1800s. I'm not going to ask you for the dates of this stuff. I just want a general time frame of when it happened. The atomic theory, John Dalton. So 1800s, early 1800s, John Dalton is called the father of modern atomic theory. So in John Dalton, the atomic theory guy, came up with 4 basic points that he had developed with his work with gases, mostly gases. And he came up with 4 basic points. And here are the basic points of John Dalton's atomic theory. And this is the modern atomic theory is based upon this. All right, 1. Everything is made up of atoms. Atoms make up all. So I'm going to kind of paraphrase this, shorten it up. 2. All atoms of the same kind are identical. All atoms of same kind are the same. Are the same. So every hydrogen atom is exactly like every other kind of hydrogen atom. That's what he is saying. Okay? No, not true. Shh. We don't want to hurt his feelings, but that's what he said. Okay, so 3. That atoms can combine to form compounds. Atoms can form compounds. So atoms like a sodium and a chlorine atom could form sodium chloride, right? Atoms can combine to form compounds, and these compounds are always found in simple ratios, simple whole number ratios. So simple whole number ratios. SWNR, simple whole number ratios. No, so I just abbreviated that. But what does it mean? Well, if you have water, for example, good old high quality, made in America H2O, Waterboy 1999. Adam Sandler, not great movies, but that one was decent. It was decent, okay? Watch it, Waterboy. H2O. This is a whole number ratio here of 2 hydrogens and 1 oxygen. That's a 2-to-1 ratio, whole numbers. You don't see water written as H2.5O1. That's crazy talk. You can't have half of a hydrogen. Either you have a hydrogen or you don't. So you have 2 hydrogens, 1 oxygen, nice whole number, no decimals, ratio of atoms. We can actually get H2O2, that's hydrogen peroxide, and that ratio, if we had H2O2, would be a 1-to-1 ratio. 1 hydrogen for every oxygen, instead of the 2 hydrogens for every oxygen of water. So but they're both simple whole number ratios. And so that's what we get. And there's actually a couple of laws that John Dalton developed called the law of definite proportions and definite composition, multiple proportions. And we will get to those shortly. I have a couple of videos for you on that. All right, so, okay. Oh, wait, there's one more. One more. All right. Chemical reactions occur. Chemical reactions. Oop, and RX. Chemical reactions occur when atoms rearrange themselves. Atoms will separate, join, so they can join. Chemical reactions occur when atoms join, separate, spell it correctly. S-E-P-A-R, separate, not separate, okay? In 4th grade, I made that mistake, and Miss Nothnagel, well, I had a crush on Miss Nothnagel. I was like so bummed, and she got married during my 4th grade year. I was so upset. I was heartbroken. First crush, heartbreak. Miss Nothnagel, 4th grade. What am I babbling about? Oh, yeah, okay, in that class, yeah, she made me write it out 50 times. It might not have been 50, but it was a lot. And because I kept spelling it with the knee, okay? Separate, spell it right. Miss Nothnagel would be upset with you. Separate, chemical reactions occur when atoms join, separate, or rearrange. Rearrange themselves. Rearrange themselves. My writing's not good today. Sometimes my writing is good, sometimes it's a little messy. It's a little messy today. I don't know, maybe it's too much caffeine. Okay, rearrange themselves. Of these 4 major points, let's see if they're true. Let's see which ones are correct. Which ones hold water for what we know today about atomic theory. Remember, this is John Dalton in the 1800s. Okay, well, you're going to give this guy a break. Okay, he was like the man, the myth, the legend. Not everything was right, but let's see which are. Number 1, atoms make up all stuff. Yep, good. Check. You got it. All atoms of the same kind are identical. Wrong. No. Thanks for playing. This is not correct. We know that there are things called isotopes. Isotopes. Isotopes are the same atom, but different forms of it. Like, for example, hydrogen has 3 isotopes. Okay, 3 isotopes. And so hydrogen can be hydrogen 1,1. And this means the atomic mass. This is the general way of writing an atom. So let me get rid of Democritus here, and I'll make this bigger. So hydrogen can be these 3 forms of hydrogen. Okay, so we're going over isotopes here. It's on the list. Okay, we need to know it. Let's do it now. Get her done. This is normal, high quality, made in America hydrogen. The atomic number is on the bottom. Now it's hydrogen because its atomic number is 1. The atomic number tells you what atom kind you have. Are you hydrogen? Are you gold? Are you silver? It depends on what this number is. And this number is the number of protons. And the number of protons identifies you as who you are. You are who you are because of the number of protons. If you're helium, you darn right better have two protons. And if you don't have 2 protons, if you have 3, don't be thinking that you're helium. Okay, if you have 3, you might say, oh, I'm helium. I have 3 protons. No, wrong. You're wrong. You're a delusional person because you are really lithium. Okay, so the amount of protons determines who we are. Now, every one of these hydrogen forms has 1 proton, and therefore we are hydrogen. However, if we look up here at the mass, this is the mass number. Okay, the mass is the total amount of protons plus neutrons. Those are the things that have relative mass, protons and neutrons. Okay, this should be a repeat for you. Okay, you should have had this probably back in like 7th grade, but we're repeating it. So we have the mass number is the amount of protons and neutrons. Those 2 have relative mass. The electron has no relative mass. Now, does the electron have mass? Of course the electron has mass. Remember earlier we talked about matter. If you're matter, you have to have mass or you're not matter. And electrons are matter, so they matter. Electrons are important. You matter. Oh, thank you. Electrons have some mass to them. Now, we give them a relative mass of 0 because they are so much less massive than protons and neutrons that relatively speaking, they don't have any mass that is going to contribute to that of the atom. But they do have mass. It's on a magnitude of negative 10 to the 31. That's a lot of zeros before you finally get to a number, negative 31, for the actual mass in kilograms of an electron. But they're so little, so not massive that we just say, not counting you. You don't count. Okay, so protons and neutrons are up here. That gives you my atomic mass. Normal high-quality made-in-America hydrogen has a mass of 1. Now, if it has 1 proton, and we look at this is the total mass of 1, you take this top number, subtract the bottom number, you get how many? Come on, Susie, you can do this. Because protons and neutrons on top, protons on the bottom, you subtract these 2, you get the amount of neutrons. I knew you could do this, Susie. You get the amount of neutrons. How much does normal, high-quality, everyday hydrogen have? How many neutrons? 1 minus 1 is? 0, okay? We want to verify. Trust but verify. Ronald Reagan, great American, trust but verify. Okay, so 1 minus 1 is 0 neutrons. Let's go to a form of hydrogen that has an atomic mass of 2. It's actually called deuterium, a duet. 2 people are singing. Deuterium has 2 mass particles. Does it have any protons? Of course it does. It wouldn't be hydrogen. It wouldn't exist without a proton. So it has 1 proton, but 2 mass particles. 2 minus 1 is 1 neutron. Subtract those 2, you get the amount of neutrons. 1 neutron. It's radioactive, by the way. Okay, we'll come back to that. So hydrogen 3, called tritium, Doc Ock, Spider-Man, if you're a Spider-Man fan, you know what I'm talking about here. Tritium, 3 particles, tritium tri, 3. 3 minus 1 is 2 neutrons. 2 neutrons, 1 neutron, no neutrons. This is the vast majority at 97 point something percent. And there's a little bit of this and a tiny bit of this in nature. This stuff is found in nature. All 3 forms are found in nature. So all 3 occur naturally. These 2 are radioactive. They're radioactive. They give off radiation. Now, we're not going to go into radiation kinds in this class. It's just not what we do. It's not part of the curriculum. However, these 2, radioactive, okay, rare, not common, common. All right? So I'm going to hold on to that and keep these up here. I'm going to come back to these in just a second. But they are different forms of the same kind of atom. It's different forms of hydrogen, and therefore they're called isotopes. Now, Dalton didn't know about isotopes in the early 1800s. He didn't know, so we can't blame the poor guy, okay? But he was not correct with this atomic theory statement. What about 3? Atoms can combine to form compounds. Of course they can. We know that. In simple Holonomic ratios, and I just showed you that with the water earlier. Yes, they can do that. Correct. Okay, what about chemical reactions occur when atoms either join, separate. Remember, chemical reactions can be identified by heat given off, light given off, color change is an indicator, precipitate coming out of solution. These are different ways we can see chemical reactions have occurred. And they occur if we separate, join, or rearrange atoms within a system. Is that true? The answer is absolutely that is true. That's how come we have chemical reactions occurring. Things are joining, separating, or switching positions and rearranging themselves. So good. So we're good here. We're good here. That's 3 out of 4. Okay, it's pretty good. I take 3 out of 4. If I were a baseball player and I got 3 hits out of every 4 times I came up to the plate, I'd be really happy. I'd be making bank. All right. 1 out of 3 if you're a baseball player is good. It's 3 out of 4. Pretty good. Okay, Mr. Dalton. Good job. Good job. I do want to just quickly talk about these isotopes up here. And if you look on the periodic table, let me grab my periodic table here. Oh, excuse me, sorry. Sorry, I didn't mean to, social distancing. I know, I'm sorry. Okay, periodic table. Copy of the one I had loaded in for you. If you look at hydrogen and you look at its mass, okay, hydrogen's mass is, it's on, when this periodic table, it's on the upper right on the periodic table of each element, 1.00794. 1.00794. The mass is 1.00794. Wait a minute, you said something about simple Holonomic ratios. Either you have one of an element or you don't. How can we get a 1.00794? How can we get part of a hydrogen? That makes no sense. You're lying. You're lying to us. Well, first of all, I'm not lying. I am standing. Okay? Thank you. Second of all, take a look at the different forms, the different isoforms of this element. If this one occurs 97%, this one occurs 2%, this one occurs less than 1%, 1% of the time. If we take what's called a weighted average, not just averaging the masses. If we take the mass 1, mass 2, mass 3, add them all up, okay, 6 divided by 3, 2, we'd get a mass of 2. Well, that's not the way it's going to be. If the vast majority of hydrogen is this form, the lightest form of it, then the overall average mass is going to reflect that 1.00794. Okay, the percentage of this low in nature does increase the overall average, called the weighted average, up slightly above 1. That's why we have those decimal form masses of every element on the periodic table, because there are isotopes for all of these elements. Another example of isotope is carbon. Carbon, you've heard of carbon. Of course you have carbon-12. This is normal, high-quality, made-in-America carbon. But there is also carbon-14. It's radioactive. In fact, it's used to radioactive dating. So it's used in radioactive dating of organic materials. And you've heard of radioactive dating, carbon dating. You've heard of carbon dating. Carbon, hydrogen, go to a movie on Friday, get together, have a little good carbon dating. Get there. Okay, moving on. All right. So that is a little bit of atomic theory. We went into isotopes, talked about average weighted masses, and I think we'll wrap this first atomic theory video up and call this one a day and take a break. All right, because I need to eat that pear. I'm getting hungry.